The next session, as I kind of mentioned, is for people that shared their challenge code. And what I thought would be good is if those people could share that with everybody. So I really appreciate people doing this, because obviously it's sharing their code, and that's always a nervous thing to do. But the idea is we'll give each of them sort of 10-15 minutes. Quick, I should have had this prepared, but I don't. So let me just see if I can grab it quick. I was going to share what the actual coding challenge was. Let me see if I can get it.
If you can't find it, I put it in a slide. So.
Have you? Awesome.
Yeah, I have. Yeah.
Okay. Leah, you were at first as well, so you can do my job for me. That'd be
Share my screen. This takes a while. Right. Can anyone see the presentation?
Yep.
Great. I'll get started then.
That's fine. Cheers, Leah.
Thanks for the introduction, Chris. So hi, I'm Leah, and I'm here this afternoon to present my solution to the most recent MLUG Coding challenge. I thought I'd start by introducing myself. I'm a process development engineer at Renishaw, and there's a few other Renishaw people here today. Hello to you all. So I work on positioning coders, one of those things down there on the screen. So I'm involved in the processes for manufacturing and test, and also some design stuff, and I've got an engineering background. And I thought I'd mention that I'm a Midlander, seeing as this is the Midlands LabVIEW user group, but not at the moment. I live in Gloucester, but I grew up in Warwickshire, so I used to go to the physical meetings back when they were a thing. So I've got a 10-minute slot, so I'll talk about the problem, I'll go over the maths briefly, and talk about two of my solutions, because I had a go at solving it a few different ways. And I won't be watching the chat, so if you do have any questions, just feel free to shout them out or go through them at the end. So this is the problem. It was set quite a while ago, and I'll read it out for you. So I went to the supermarket to get some beers for the Euros final. So you can, this is a recycled one. And my bill came to £11.99. With the money detailed in this Excel spreadsheet, how many combinations are there that make up the exact change to pay the bill? So you can see we've got a wallet with 42 different coins in, and they come to £31.50. So when I saw this question, at first you think, oh, that's just, stats, maths, probability. I know all of that, I can do it. But then when you start trying to solve it, at least I found it quite tricky. So the first thing that I couldn't really decide on was, does it matter when you've got, say, 5 1p coins? Is giving these two different to giving those two? Like, is that a different solution? So that was just something I had to consider, whether identical coins count as identical or not. And also how I'd prove to myself that the answer was correct as well. So those were just issues that were there in my mind. So at first I just thought about if I could brute force this, like check all the solutions and just see if they're all right. Because some problems like chess, that's pretty much impossible, but other problems it is possible. So talking about earlier what I said about the same coins, are they counting as the same here? So if you said that 2 identical coins of the same denomination were different, I just thought about it as for each of the 42 coins, you either have it or you don't have it. And so I calculated that there's 4.4 trillion different combinations there. So that sounds fairly difficult to brute force. Hope I did the maths right. But then if you assume that it doesn't matter which identical coins you select, what I did is I said for when you've got 1, you can either have 0 or 1 of them. When you've got 3 coins, you could have 0, 1, 2 or 3 of them. So if you add 1 to each of the quantities and then times on the numbers together, I got 4.4 million. So like that's a bit more doable. And it's literally, a million times fewer combinations to check than the other way of doing it. So the first solution that I did, I just basically thought about the most simple way of solving it, nothing fancy. I'll show you the code. Let me get So this is my nested loop solution. And basically what I'm doing is I've got my wallet with all my coins in, and I've got a load of hard-coded loops. So each of the quantities of the coins is how many times the loop will iterate, with the pennies in the middle and the £10 notes on the outside. And basically I'm using the iterations to just count up basically in to the maximum of each denomination of coin. So what I'll do now, I'll just quickly disable this conditional terminal, and I'll drop a wait function in just so you can see what's going on a bit better. Way of doing it. So if I just run this, you'll see what's going on. Like I'm counting up to the maximum of each coin, basically the maximum quantity of each coin. So I'll just delete that wait function. So you can see there are some problems with this solution. Like say I added a £20 coin in, a £20 note, sorry. I'd have to draw another loop, and that's not really ideal. But it is pretty fast doing it this way. So if I turn off my I'll update the display first, and basically I can go through pretty fast in 2 seconds and get a big long list of solutions that I've just put into an array that I've already made. So for each one I'm checking if the amount for the coins is equal to the goal amount and adding it to the array if it is. And if I don't update the display, it's even faster. And earlier when I wasn't sharing my screen, I was getting it in 0.4 seconds. Not at the moment, apparently. But yeah, I was quite pleased with the speeds of that. But you'll notice, that earlier I undid the conditional terminal. So what that's doing is in 0.8 seconds, I'm crunching through all of those 4.4 million combinations. And it will be quite complicated. Like in certain situations, you know that you've gone over the total, but you're still counting up. But rather than putting conditionals on each one of these, I'm only doing the evaluation in the middle loop. So I can speed that up slightly just by, if the pennies are over, not adding any more pennies. And that actually surprisingly, it did bring the time right down anyway. Let's see. Yeah, 0.4 seconds-ish. So yeah, that's a solution, but I started thinking about how I can make it a bit better. So next, I decided to try and make this recursive, just so if we change the question slightly, it will be a bit easier to modify. So all I've done here really is I've taken that outside loop and I've just made it into a recursive VI. And then so it's either adding in another loop if you haven't done all of if you're not at the penny stage, and if you are at the penny stage, then it's got that middle loop with the conditional terminal. And I quite enjoyed writing this because I don't know about you, but recursion was something I learned about, and I did it once for a noughts and crosses solver, but since then I've never found a situation where I can apply it. So yeah, maybe it's just because I'm not really looking for it in my job most of the time. So in terms of how this performs, yeah, it's pretty similar, maybe slightly slower. But I get the same answer, 2,184 solutions. So yeah, that was another one of my improvements. If we've got another minute, I'll just show you another one of I tried doing a few more complicated solutions as well. This one was just quite fun. I was just using quotient remainder to make it count up in the way that my other VI was doing. But it's actually a lot slower, even though it looks quite nice. It's a lot slower just because you have to, the way I'm doing it is I generate it in columns, and then I have to make a separate loop because I basically want the array the other way around. I don't know if I explained that right, but basically I couldn't do it all in one loop. So that one's not ever going to be any faster. And I did one as well that's a bit more of a clever way of searching, like not bothering. It's a breadth first search, but it knows that if it goes over the goal amount, not to keep looking. So it's got a nice animation on it, but it's just incredibly slow, basically. And you can see that in this case, I'm saying that different coins of the same denomination give different values. But yeah, I just have a soft spot for this one because the results look quite nice as they're coming out, the way it's searching. Yeah, so those are my solutions. That's all I've got to show you, really. But yeah, I'd welcome any questions that you have.
I like in that last one where it says bingo when you get the right answer.
Yeah.
Thought that was cool.
Yeah, because what you don't see is it's actually saying like too high and too low, but I think I've turned off display updates to try and make it a bit faster. Like I left it running for a few hours once, but it was just nowhere near getting all of them, so gave up.
Neil says to run it on FPGA, presumably you didn't have one available.
Yeah, I could have done that. I've got yeah, my Rio somewhere.
Okay, yeah. Awesome. Good stuff. Any questions, guys?
Did anyone else here who's not presenting have a go at this one, or did it pass you by? Because I think they're normally posted on LinkedIn, aren't they?
Yeah. Yeah, we normally share them. Okay. Well, thanks very much, Leah. Really appreciate that. That was awesome to see it in the flesh, as it were. And thanks again. Yeah, nice one. Right, I'll pass over to Louis, sorry, if you're there. Yes,
I'm here. Hi.
Awesome. Right, go for it. Then I'll let you take the floor.
So, contrary to Leah, I didn't make any presentation. I only made the code. So I will share my desktop. So I think it's this one. Yeah, I think I'm not sharing my desktop.
Yep, we can see your file explorer now.
Yeah, but it's only my file explorer.
Yeah.
I have to share the screen. It's better. Okay, so to solve the problem, as Leah referred, so there are the possibility of making brute force, and it's this one. It's optimized, but it's 4 million possibilities, and it takes like 9 hours. But I made other solutions. So I opened a file. I created a simple VI to read the Excel file. What?
Nice.
Wrong place. No. So it reads, and I made the connection with Python and DLLs. So the brute force is like Leah made. So it's in LabVIEW, and it calculates the possibilities of the 2 million possibilities, and it gives, for each possibility, it gives one coin of 5, for 3 of 2. It's for each possibility, it gets the coins that necessary to obtain this price. Using a DLL, it only calculates the possibilities, but it's very fast. And these three those that are made on Python, and it's also made on Python. This one, all of these use dynamic programming. So they use a table to make the calculations. So I can show you the code. So if you use brute force, it's in here, brute force. So if you use brute force, the code gets to the money, and it calculates calculates all the possibilities, and it multiplies the array of possibilities with the array of money. and that one gives a vector with all the amount of that money that is with those coins, and taking that into account, it can determine the result. For the root, for the others, so for instance, for the Python, so the combination on Python calls a def function, and for Python, I normally say that it's better to use. So you have, when installing Python, you have to be attentive to the bitness, because if you have LabVIEW 32 bits, you have to install Python 32 bits. So to develop the code, I normally use Visual Studio Code that is free. So as you can see, in this is the def for one of the Python files, and this is the other one that is very small. And this code is for testing. So you can run the code in Python to test it, or you can call it on LabVIEW and call the function, giving the parameters, and you receive the output. The output can be only one, but it can be tuple, so you can put in the tuple several elements. For DLLs, afterwards, I made a DLL, so it's a C DLL, and for that I use the tab C. So let's see if I have it in here. So I have coins DLL, coins CPP, coins layout. Okay. So I made a little DLL. You have to make another file, and this is the code. All of these codes are dynamic programming, so they are extremely fast. And this code is exactly the same as the one used in Python. So I tried to move it to make it compare it. One thing to be attentive is that when you compile, you have to choose the 32 bits, because my LabVIEW is 32 bits, so I have to choose the correct version. And I think that's wraps all of my presentation.
That's awesome. That is really, really impressively. That's amazing. It's great that you've used lots of different methods of doing it.
Yeah.
Anyone got any questions on that stuff?
Anyone?
Do you do a lot of projects doing Python with LabVIEW, like combining the two?
Yeah, previously I wasn't using Python, but now I'm using more Python, because there are certain things. For instance, when you use a camera to detect a person, it's really easy in Python, and so you can send the result to LabVIEW. And for instance, if you have a camera in LabVIEW to detect the movement, in Python it's easy to detect it, and you send the results to LabVIEW, and LabVIEW can knows if there is movement in the camera.
Oh, great. Yeah, thanks for the presentation.
Do you find it easy when in Python you have to use other Python libraries, and like when it's more than one file?
Yes, in OpenCV, if you use Python, so in here, I'm not using any libraries, but if you put it in the beginning, import some library, you can use it in the functions.
Okay.
Neil's just nominated you for another presentation as well on LabVIEW and Python. So I'll be talking to you about that later.
Yeah, thanks.
Awesome. All right. Well, if there's no other questions, we'll move on to Adrian. If you're there.
Yep, that's me.
Awesome. I'll hand over to you.
Yeah, let me I do have a presentation with me, so I think it's better if I just share the screen. So I can switch from one to the other. Okay. Yeah, so as opposed to these other two guys, I only have one solution. I didn't do more than one. Sorry about this. What I did instead is to look for other VR challenges. So just so you know, unrelated to LabVIEW, there are many interesting VR challenges out there. The maximum number of beers that someone can carry is 27, which I think is quite a lot. The second one that I find very impressive is that the maximum number of beers that have been drunk without passing out is 127, which I think is unbelievable. And the last one is that the minimum time on drinking 1 liter of beer is 1.3 seconds, which hasn't been beaten since 1977. Now, this is very exciting. This one is even more exciting, our challenge. And Leah explained what it is about, so I'm gonna skip this. I changed the format of the Excel file into CSV just to read it, because why not? And the first decision that I made, I think different to these guys, is to put all my cache into a cluster. And this has a lot of implications because the code becomes more readable, probably, but at the same time is way less scalable. Yeah, because each of your nodes is not on an index of an array, it's an actual cluster, so it's an actual element of the cluster. So you cannot do a recursive BI like they had done, for example, which is a pity. But yeah, you can read it quite easily. So you can see here that all I do is I populate this cluster with what is on the spreadsheet, and then I do basically the same thing that Leah did at the beginning with all the loops one inside each other. It's just that they are sub-BIs, slightly different to each other, which is annoying. Just one disclaimer, the solution that I'm gonna give you is actually wrong. But moving into it, what I did was, it's kind of brute force, but almost. So I just thought, well, if I start with the biggest nodes and I try to use as many as I have, and they are not over, and they're over the maximum, the build that I want to meet, then there are too many, so I have to try one less, and then one less, and then one less, until I'm below or equal. If I'm equal, then I have a solution. If I'm not equal, then I will stick to those number of nodes and then try with the lower node and do exactly the same thing and keep recording every time that I get a match and continue trying one node less and more smaller coins, if that makes sense. So that's what I have done effectively. So what you see here is that happening. I take the whole cache, which is in my cluster, and then I make a new cluster which has no cache at the beginning, and I start populating it with nodes and carrying it over to the sub-BIs, and so it remembers what it has had from before. And then I just concatenate all the outputs that are valid. So as you can see, this is a problem because you can see this BI, and if you see the next BI, which is the one for the £5 iteration under here, it looks really similar, but because I'm using a cluster, the element that I need from the cluster is different, so I cannot really reuse the sub BI, which is annoying. So I had to do, as you can see on the left, 10 BIs that are like Leah's 10 loops originally, all identical almost. So the code is not great, really, if you think about it. It's not scalable, but I assumed that it wasn't going to grow and we're not going to have more different nodes. So I thought it was OK to go this way and it would make it readable. But thinking about it, an array is probably better for this. Yeah, and on the other hand, having a cluster with the cache is quite neat. Yeah, so for the £5 and £2, they are all effectively the same. What you can see here is just that. And if I move on, at the end of that, I just have just a for loop, checking all my combinations and checking that they are valid and displaying them. And I will show you the code in a second. Yeah, so if I show the code, which is here, Yeah, you can see that it takes 0.4 seconds, so it's pretty fast compared to the others. And it gets the right answer now after I have done some fixes that I will changes that I will show you in a second. And if you look in the inside, all I do is that what I explained before, I take the values, I put them in this cluster, I send the cluster over, and then I generate the combos, which happens. Then I measure the time in here. I have this just to stop the process at any time. And yeah, and what you see inside is what I told you. For £10, you check, you take one less, you check, you take one less. If it's valid, you add it. If it's not valid, you don't. And if it's not meeting, it's less than the value, then you go for the £5, and then this looks the same, and then you go for £2, and it's the same, until you get to the bottom. Yeah, so that's how it works. And yes, and then I check the combinations and put them in this nice array, so you can check. You can check all of them. You can check how much cache you have used, how much cache is left, and what was the original cache, and whether the solutions are valid or not. Yeah. So that's that. And interesting things that I found is that my original answer was 1,164, and that was wrong. It's 2,184. And the reason Leah told me, so Leah has all the credit for this, is that you should never compare float numbers, obviously, because yeah, you just don't do it. So that was my first mistake, which is very useful to prove why you have to use sub BIs and reuse code as much as you can. Because if you make this silly mistake and you put it in 10 BIs, then you have to make changes on 10 BIs, which is not great. So I had to make this little change just to fix it, and then check the answers, and still a bit higher, but not quite. The reason being the same thing, almost, that when I'm checking if it's bigger or equal, I also use the floats. And if the equal solution is somehow treated differently, you are not going to get the right answer. So don't use plus equal if the equal actually matters with floats. So that was my problem there. Well, you can use it, but you have to be careful, because in this case, it didn't work. And again, I had to make this little change here at this OR gate to make it work. And I had to do it 10 times. Not great. And then finally, I got the answer. So I think that's the main learning lesson from this solution that I have. First, choosing how you structure your data is really important. And in my case, choosing to use a cluster, I believe, was the wrong idea. And second, make your code as scalable as possible, because even in a small exercise like this, when you don't, you then have to change things in multiple places, which is not great. And that's all. Thank you.
Awesome. Thanks, Adrian. That's awesome. That's really interesting to share the way that you've gone about it and the challenges you came up against. I'm sure people will find those really really valuable. Anybody got any questions on Adrian's solution? Sounds like it's a familiar problem with the using doubles.
Yeah, classic.
Awesome. Okay. And last but not least, Petru, hopefully you're there. Yes.
Hey, Chris, I am.
Right, I'll hand over to you then, if that's all right.
Sure, thank you. I'll go ahead and share my screen then. Hopefully, you can see a presentation now.
Yeah, we can see that.
Thank you. Sorry, I pressed the wrong button. I'm just trying to start a presentation again. Okay. So first of all, hello everyone. My name is Petru. I also work for Renishaw, just like Leah and Adrian, and I'm also a process development engineer and a CLA. And I would like to thank Leah for popularizing this challenge and making me aware of it. And I thought it was a very interesting coding challenge when she posted it in one of our internal work forums. So yeah, it was a very interesting problem. Here I copied the original problem statement, but since we've gone through that already, I'll skip through this. The answer I got from my one and only implementation is 2184. And I will now give a demonstration of the code. So I will open LabVIEW, and the code is in this little project. The project doesn't use any libraries because I thought it's probably easier to share code that way and not have too many dependency issues. And it has one main VI, which is this VI here. And if we run the code, then we should see the answer popping up here. Yes, 2184. It took 2.6 seconds roughly, and it also lists the solutions in a format that's quite human readable, I think, which is quite nice to be able to test and debug and verify that it's doing the right thing. And you can see it's quite a long list of results here. And now I will go back to the presentation to give an overview of what the code is doing, and then I'll try to show the source code itself. So if I go back to the presentation, then I first need to mention that just like Leah mentioned previously, one of the I think important questions that, or important decisions that needed to be made when starting to create a solution was whether the coins are uniquely identified or not. So just like Leah mentioned, whether say if you have 2 1-pound coins, are they classed as being the same in terms of a solution, or are they classed as having like a unique ID or a unique name associated with each one, or a unique identity? And I decided that we probably don't want to have a unique identity for each coin, just like I think everyone else did. I decided to represent all money values in pence or penny, and that allowed the use of an integer rather than doubles. And I think that has the benefit of not comparing doubles, but also optimizing and speeding up the code. And in terms of data structures, the two most important data structures used by the code is an array that I called money available, and it's abbreviated as MA in the code. This essentially represents the wallet that we get given. And it's made up of an array of coin instances, and each coin instance is a cluster that contains a value in a penny, and a flag associated with it. And I'll come back to the importance of that flag. The money available is sorted by value descending. So you can see here in the screenshot, these are the first elements in the array when it's populated with the original problem input. Because you might remember we had a 10-pound coin, a 10-pound note, which is represented by this 1,000 penny value. And then we had one 5-pound note, which is a 500 penny. And then we had 4 2-pound notes, and you can see 4 instances here, and then some one-pound coins and so on. And the second most important data structure is the money selected, which is abbreviated as MS in the code, which is the money that we currently use in our solution at the moment, and that money may not yet reach our target, but it's something that we keep adding to in order to reach our target, if that makes sense. And this money selected is basically a list of references or indexes that point to the money available array up here, and I found that's the most optimized and efficient way of doing it, rather than storing possibly the values of that were selected themselves, you can better store indexes to the values in money available. And also we store here the sum of the total of all the elements selected in the coin selected array, and that is an optimization to save us from having to recompute that sum many times over the algorithm. We only update that sum when we actually add or remove a coin from this list, which is another optimization. And the implementation is a state machine, contains these 5 states. So in that sense, it's a very simple implementation, and an easy description, but not necessarily fully accurate description, is that the state machine tries to select coins from the money available list until we meet the target. So in the original problem statement, that was £11.99, which would be equivalent to 1,199 penny. If the target is exceeded, then we know we've got too many coins in, that we select, so we need to remove one and try another option. And we need to keep track of which coins are selected at any given time, and also we need to very importantly keep track of which paths in our search space, if you will, we've already explored, so that we don't repeat them over and over again, and we can actually keep track of where we are in our search space. And at each stage, I decided to select the largest value coin that is available, that hasn't yet been selected. And this has the consequence that the program finds the solutions that use fewer larger coin values ahead of solutions that use more smaller value coins, if that makes sense. So it has a bias towards finding solutions that use large coin values ahead of small coin values. And this, in effect, is actually a depth-first search algorithm. And actually, that's the reason I thought this challenge is so interesting, is because it's a depth-first search problem, really. This DFS is a powerful technique for solving a large variety of problems. And some examples are the challenge at hand, maze solving, tree traversal, and the night tour problem, which is another application I worked on previously in my own time for fun. And there's a link here to a YouTube video discussing that if people wanna have a look. And I find DFS interesting because it is a very intuitive human technique, I find, in the sense that it actually replicates what a human would do if they were if they would try to solve these kinds of problems by hand. I think most humans would empirically approach the problem in this kind of way. So I find it very interesting to try to formalize that process in a computer program. And a great benefit of DFS is that it uses a finite and relatively constant amount of memory, regardless of the size of the search space, which is actually very, very important, because it means we can approach very, very large search spaces with this technique. It will take longer if the search space is very large, but eventually the code will get there. It won't run out of memory. Whereas a breadth-first search, which is the alternative to DFS, is a very useful technique as well, but the amount of memory it's forced to use increases proportionally to the search space that we are searching through, which actually makes this approach, the BFS approach, completely unsuitable when you have very large search spaces, because even if you have a supercomputer with terabytes and terabytes of RAM, there are some search spaces out there, some problem inputs that would prove simply too much to handle with BFS. So in my experience so far, I found that DFS is a much more practical technique than BFS. And here I try to show two simple examples of the challenge at hand, where the wallet we're given is much simpler, contains much fewer coins than the original problem input, such that we can actually solve these problems by hand or by eye. and for example, in this scenario, we have a wallet where we have 1 2-penny coin, and we have 3 1-penny coins for a total money available of 5 penny, and a total number of coins available of 4 coins. And the challenge is to find all the solutions where we can pay out exactly 3 penny with the coins at hand. And you might have solved it already in your head. It's very easy. There are only 2 solutions. One is where we use 1 2-penny coin and 1 1-penny coin for a total of 3 penny. Second solution is to use all 3 1-penny coins for the second solution, and the order in which the solutions are listed corresponds to the order in which my implementation would find them as well. Whereas again, it will find the solution that uses fewer coins first than the other. And I can show that in the code if I maybe clear the array, and if I set up the inputs to the problem inputs we've just looked at. So we have 1 coin of value 2 penny, and we have 3 coins of value 1 penny. So if we run this, then we find the 2 solutions we've seen before. And another example, simple example, but slightly more advanced, is we have a few more coins now, and our target is different. It's 7 penny, and I won't read out the coins we have. I think you can probably just read them from the table, hopefully. And this actually leads to 4 solutions, which are listed here. And I will try to set up this example in the code as well. I hope I remember the the number of coins. Yeah, so I can type them in here. So the target is 7 penny, and we have 1 3 penny, we have 2 pennies, and we have 4 coins of 1 penny each, and we get the answers here just like that. And I found these kind of simple, very simple examples to be very useful to me when debugging and testing and understanding the code. And I've reached the end of the presentation, so I'll go into the code in a second. Just wanted to mention that I've put the presentation and the code. I've made it available in a OneDrive shared folder, so feel free to follow this link to download the presentation and the code from there. And I will go to showing the block diagram. It's not necessarily the tidiest code possible. I'm sure it could be made more tidy. I did try to add some more comments in the code and in the sub-VIs for anyone that would possibly try to have a look at what the code is doing. It is a state machine, just like I've mentioned. It has these states, and this state machine implements a DFS algorithm, basically. There are some optimizations that I intentionally haven't made in this version, because I found that optimizing the code to its furthest extent, or well, I'm not sure I could find the true optimum, because I think that's quite elusive, but optimizing it more than it is now actually leads to code that's less readable, and I found that's sometimes a trade-off between readable and optimization. So in this case, I think I struck a balance where it's still fairly readable, hopefully. And I also went and tested the code with a bunch of different problem inputs, some of them much more that actually represent much larger search spaces than the original problem input. So they take much longer for the code to find all the solutions, but it does find them. And I would like to show maybe this input. So I will copy the values from this test vector into the front panel input. So we'll paste the data here, and the target there was 400p. And just to discuss what I'm doing here, so this is an input where imagine we have a wallet that has quite a lot of different coins. So we have four 50p coins, we have 10 20p coins, 20 10p coins, and so on. And our target is to accumulate 400p. And I will run this. This I think takes just a few seconds still, not too long. But you should find quite a few thousand solutions to this. Okay, it's still running. Hopefully it's not too slow. It should finish fairly quickly. Okay, still going. Okay, it's taking its time. I hope it's actually gonna find it at some point. I'm just a bit worried. Yes, sorry about that. So what it's doing is it is finding some solutions, but I actually I mistakenly took the target of 400 from another example or test. The target should have been 200 here. So yeah, what I'll do now, I'll change the target to 200, and that will change the execution. We'll make it solve much quicker. Okay, still taking a bit longer than I remembered. Okay, it's finally finished. So it's found 69,000 solutions in about 15 seconds roughly, and here you've got a breakdown of how many seconds per second. So sorry, solutions per second. So this is a good measure to test any optimization being made to the code. And again, we have all these solutions, 69,000 solutions listed here roughly. And again, it's a very good way of understanding how the algorithm operates and the order in which it finds the solutions, and that it doesn't find any duplicate solutions and so on. And I think I'm getting very close to the end of my 10 minutes. And unfortunately, I know that I haven't really gone into these sub-VIs, so I haven't really explained how they work. I think that's quite an in-depth discussion actually to make them justice, really. Not because they're super complicated, but still I don't think they're trivial either. So I think I'll just leave that for whoever wants to inspect the code in their own time. Okay, thank you very much.
Petru, that's awesome. Thanks very much for sharing all that. There was just one comment. If you could drop that link into the chat, that would be really helpful for a few people. That'd be awesome.
Sure, absolutely. I'll do that right now, actually.
But yeah, massive thanks to Leah, Lewis, Adrian and Petru. That's amazing. Really, really helpful to sort of share all that stuff. There's a good couple of things that I've learned out of that, and also some new stuff. So every day is a school day, which is I love school days. Unless it's a home school day, that's a different story altogether. So yeah, any questions for anyone? And I guess the guys who did the coding challenge, any questions for your fellow coding challengers? Because I guess you've kind of seen other people's approaches. It's probably quite interesting to see that compared to yours.
I just wanted to say to Petru, thanks for confirming that the breadth-first search wasn't going to work, because like I don't know enough about this stuff. I just tried it and left it running for a few hours and didn't get anywhere. So, yeah, I need to read some books on it.
Yeah, I think I came across, while reading about DFS, I came across BFS, because they kind of go hand in hand sometimes. And I bet that for relatively small search spaces, it would work, but it's just something that I think to keep in mind, that whenever there's a very large search space out there, for example, if there would be a wallet that had, say, 1 billion 1 penny coins, and the target would be to find all the combinations that result in 1 penny output, then obviously it's kind of trivial that there's only one combination. But I think possibly a breadth-first search and a brute force approach could actually try to examine all those possibilities before they discard them. So they would have to keep in memory 1 billion combinations, and that might make the program run out of memory.
Awesome. All right, guys. Well, if there's no other questions or comments or anything, then that kind of brings us to a close. Just a massive thanks to all the people that presented. and I'm going to endeavour to get another coding challenge out for next MLUG. So all those that have been inspired by these guys doing theirs, they can get involved. And I'll try and make it equally as tough, I think. We can't go easier. We can't go easier than that, can we? So yeah, thanks everybody for coming along. And we've got our date for June, which is, let me just get that, make sure I get that right as well. Jenny will slap my wrist. I think we're going to the 9th. Let me just double check that. Yeah, 9th of June. So we've got a couple of possible presenters for that, but we're always looking for people that have got stuff to talk about. So if you have got something, then just drop me a line and we can fit you into the next one or the one after that, yeah, sort something out. So yeah, we'll see you next time, and take care of yourselves.
Cheers, Chris.
Cheers, guys.
Bye.
See you later. Bye.
Bye.
Thanks everyone.
Nice one.